I'm Quentin Teegarden, and I'm here to talk to you about Kotlin multi-platform. Oops. If you came for a talk where I'm going to convince you that Kotlin multi-platform is going to solve the world's problems, this is probably not the right talk. We're just going to talk about the fundamentals of Kotlin multi-platform, Compose multi-platform. We have 30 minutes, so we're really going to be barely scratching the surface of this. Hopefully just start to dispel some myths about it, how it works, and then I'll share a few of the things that I've done as a learning opportunities for folks here throughout. To start, we're going to go through what's the difference between Kotlin multi-platform and Compose multi-platform. We're going to talk about the compiler and how it all really works. When we get into the Compose side, we're going to start to break off into really start to think about what this looks like for iOS as well. Kotlin multi-platform, Compose multi-platform runs beyond iOS, but since our group here is very mobile focused, a lot of the stuff that we're going to talk about is going to be heavily mobile focused. I'll demo this a little bit, this little game that I built. This is all built using Compose multi-platform. Runs on iOS, Android, JVM. This here is actually a Mac OS desktop app, and they also will run on web for WASM. We'll just talk about this a little bit and give you a little tour of the code and just generally what it looks like to be working in this type of space. We'll talk about some Swift interop here. This is where some folks will probably I'm going to really dig in on some of the challenges, especially when you're working in KMP and you're trying to share some code. There can be some real challenges there. And so if you're on the Android side, you're probably like, wow, this guy really is telling a bad story about KMP. But don't worry, there's going to be another slide about talking about how it's getting better and things that we can do to make KMP interop work really nice for our iOS friends when that does come up. And then last but not least, the question that we get, probably I'm sure you all hear a lot, is in the age of AI where code is cheap, does multi-platform even matter anymore? Spoiler alert, I believe it's yes, that's why I'm here. But we can talk about that a little bit more. And I think of AI as certainly it changes how we look at everything, and certainly that's true for multi-platform as well. All right, so diving right into it, what is the difference between? Okay, what is the difference between Kotlin multi-platform and Compose multi-platform? I like Rivian. I don't know if you guys like Rivian out there. So Rivian's super cool. So I like to think about their skateboard platform. So on the left is a picture of Rivian's skateboard platform. It actually is the foundation to most of their vehicles out there, and that the architecture remains the same throughout. That's really Kotlin multi-platform. The goal here is not broad, one write and it runs everywhere. It's to share business logic, to share utilities, anything that's really not UI, right? And so you can go all in on Kotlin multi-platform and still have native UI. This is where we might spend a lot of time, especially if we're wanting to leverage things like liquid glass on our iOS side, and you want to really lead out on the native UI capabilities. Jumping over on the other side is Compose multi-platform. So Compose multi-platform is built off of Jetpack Compose for Android UI framework. If you've used Jetpack Compose for Android, it's pretty much identical. Most of the Android Compose packages actually are multi-platform by default now, which is really great. And the ones that are not are continuing to be updated to support multi-platform. So, theoretically, you do it right, you can get, write once and you get it everywhere. And it works pretty well. We'll run on iOS, Android, web, JVM, Mac OS, really, just about anywhere. And again, its goals are fundamentally different. Its goal is to write it once and run anywhere. It doesn't mean that you have to go all in. Compose multi-platform is flexible in such that I can have Swift UI on one screen and Compose UI on the next screen. That's certainly possible. It is really up to you to drive just how much or how little you plan to use it. But the primary thing I want to hit home here is that really it's Compose multi-platform is optional. You do not have to go all the way Compose multi-platform. It is built on the same foundations as Kotlin multi-platform. You can mix and choose and do whatever you want in that regard. So super flexible. I think that there's some companies out there that kind of play it on a per feature basis about whether they're going to use KMP, CMP, or fully native. Really nice to have that flexibility. All right, so how does that actually work? If you want to talk about compilers later, I love the Kotlin compiler. I've given a few different talks on the Kotlin compiler. There's a lot of really cool stuff there. But really all the magic lies in the Kotlin compiler. There's no bridge. There's nothing fancy happening. There's no JVM that's magically being installed on your iPhone when this is running. It's just everything's happening in the compiler. In fact, when Mark talks about Swift for Android later, we're going to be talking about the same underlying compiler underpinnings, which is LLVM, and that's how that's working, just going the other way. So really cool to see a lot of overlaps with that. But the Kotlin compiler, starts with Kotlin source code. There's a Kotlin compiler is broken up into a front end and a back end. The front end is kind of the thing that is always consistent. So if you're working in Kotlin, the front end remains the same. Kotlin provides the capability for you to write front end and back end plugins for their compiler. So a lot of the way that like Jetpack Compose works, actually, it's split into both a front end and back end plugin, but a lot of things happen in the front end. We do a lot of work in the front end in those plugins. This is where we're going to generate a semantically based like AST and a lot of stuff that's really not even particular to Kotlin multi-platform. Where the magic happens in terms of like how we are generating these different representations that are going to run on the various devices is all in the back end. So the Kotlin compiler back end. There's a few other layers after we get into the front end, after we get the front end intermediate code, the FIR. But ultimately, what the back end does is driven based on like what we're trying to output it to. So in this case here, we are going to work through the LLVM and we're going to get raw native machine code for iOS. And we'll talk about this in a little bit, but historically, this has meant for native machine code, and it's bridged with Objective-C headers, which I'm sure for all the folks that are working in iOS all the time, they hear Objective-C and they're like, "Boo! Don't boot me off stage yet." There's some hope for it. So, that really the limitations, like you never see the Objective-C, but that is the bridge that allows you to from your Swift code be able to call functions or interact with the KMP code that's generated. So, but the new Swift interops are coming. The big thing I want to call out here is the memory management down there. So iOS runs an ARC for the automatic reference counting. Android obviously uses a garbage collector, and the KMP actually embeds a lightweight tracing garbage collector to kind of help bridge this. So you can imagine if you are using an object that's both being referenced in your Swift native code and then in your Kotlin code that's being shared, we need to figure out like, is that reference still being used by both sides of the app, and when we can let it go and actually clean it up. And so there is a lightweight tracing garbage collector. This is probably the most annoying part about it, in my opinion. It works well, but it always kind of gives me a little bit of heartburn. But I always like to make sure like what people know, like what they're getting into and what and how it works. So that is that. Jump to the next slide. So for Compose multi-platform, again, our goal here is to run it from end to end. We're sharing UI. We're probably sharing business logic as well. You could just build with just UI, but we're likely sharing both. And there's no native wrapping here, so it's not like you have a Swift UI view or a UI kit or anything like that that composes wrapping. There's no wrapping. We're actually drawing pixels on the screen. So if you all are familiar with Flutter or Chrome and how Chrome's graphic engine works, those all run through what's a framework called Skia. Kotlin, or excuse me, Compose Multiplatform runs through what's called Skiaco, or if I say it right. And it is essentially it's just a fork of Skia. It builds on top of Skia for Compose Multiplatform to run. And again, this is how we make sure that we are getting consistent UI on both iOS, Android, web, Mac OS, JVM, et cetera, whatever you're looking for. In the world of Mac OS and iPhone, we're talking about drawing pixels directly on metal. So we're sending actual metal instructions and drawing instructions. And then same thing for Mac OS, that'll be OpenGL. So again, nothing really outlandish here. The biggest things I want you to take away from this is that we're not actually working through any bridge. So that is great. While that is great that we don't have these bridges that we're working across, it does mean that if you plan on leveraging liquid glass, you're not going to get that out of the box. There are a few folks that are trying to reinvent liquid glass somewhat for Compose Multiplatform. I would argue that you should just stick to KMP if you have those needs. So rather than going all the way to Compose Multiplatform. So there are options out there for you, but it's just your call. All right, so let's take a look a little bit at the code here. And so, but before we do that, we'll talk about this game a little bit. So this game is not anything official from Capital One. It is just a fun game that I did for another presentation. This is built using MVI and a unidirectional data flow. So we have a model, which is our state in this case. The UI in this case is very dumb. All I'm feeding it is a list of objects, in this case, the objects that you see flying around on the screen. And then I'm also feeding it like exactly where to draw. The UI is really just drawing an image where it needs to draw, which works out really well for something that is like low graphics like this. The intent is obviously the user is tapping on the screen and other actions that take place, and then things like when the ship runs into stuff and all that. And then we're leveraging Compose to also calculate whether the layers are hitting each other as well. So that's how we know to collect stars or different things like that. So so that's what you see happening on the screen. I will stop sharing from here for a second and switch to the other share so you can see the code. Maybe. Wow, that's really bright. I work on Zooms all the time. You would think that I could get that, but. All right. All right, so we're not going to dive too deep into the code. We don't have enough time to really talk about everything, but I want to give everybody a tour of like what you would see if you were leveraging, in this case, a Compose multi-platform application. This is the entire project here. We are an Android studio. You can launch this in other locations. Obviously, you can open up the project even in Xcode, but you're going to have probably a less fun time when you're looking at the things that are not Apple first. So Android Studio is great for this. So I would highly recommend you start there. First and foremost, I'm going to skip down to the iOS app. If you are launching this in Xcode, you're going to probably just launch the iOS app right here, and you can kind of see what's in here. I have the normal setup of everything you'll see, your plists and all that. That's all going to feel very familiar to you. So nothing wild there. And here, this is essentially the view that is shown. It's very light. We aren't doing, this is a really simple application, so we aren't doing anything wild. But the biggest thing here is I'll highlight is that we have this compose view up here, and it's calling this main view controller KT. That happens inside of our core shared logic. So we would find this same we'll find this same function call on the Android side and in the JVM and anywhere else that we're targeting as well. So you can see like there's actually a desktop version of this as well. We're going to expand open the Compose, and we'll see some more packages in here. And again, you see some iOS main, desktop main, common main. We'll talk about all of these here in a second. But the biggest thing that I want to highlight here is we'll open up this this common main. This is where, again, this app is, we're sharing everything in this scenario. So most of the logic is going to live inside of common main. And we want to look at that, our UI. And this is what is being built from that. So the iOS main, actually that main view controller that we were calling from iOS earlier is right here. And this is ultimately just calling app, which is what we were at. So you can kind of see how, ultimately we start in Swift when we were down here in the iOS app. When we expand that open again, we are in, we are in Swift here. And then we jump to this main view controller that's defined in Kotlin by under the.
Wait, zoom in on the code.
Oh, I'm sorry. Apologize. My eyes. Is that better?
Yep.
Yeah. All right. Sorry about that. All right. So if you starting back here, we are again in Swift code here. And where we have this main view controller that is defined again inside of our iOS main within our Compose app. This is this shared Compose app that's going to get compiled down and be shared across that. So this is the main view controller that we're calling, and ultimately this is really dumb. There's not much here other than the app function call, which is just right here. So this is the start of the whole game. So everything starts right here from this composable, and we call this build UI function, and where our view model is getting passed, and we are starting to collect on state. We'll jump into a little bit of the logic here, but before I do so, I want to highlight some of like why we see Android main, common main, desktop main, all of that right here inside of the Compose app, because the Compose app is supposed to be our, we're writing this once. Why do I have these various packages various packages? Well, I might, in here, there's a concept in KMP called expect actuals. Expect actuals allows us to define a function in the common that has to be provided in the various implementations. So for instance, in this case here, if we go to common main under platform, I'm saying I expect get platform, right? We're not providing the implementation details here, but what we're doing is leveraging the plugin the plugins in the compiler to actually validate that the targets are providing these the actuals of this, the actual implementations. So over here, we're providing just a simple iOS platform. And this is kind of really just how you can provide a lot of different details, how you might be able to, like if you are running in Compose fully and you wanted to tap into something that there's not a framework or something that, user defaults is a bad example because there are open source frameworks to cover that. But if you wanted to use tap into user defaults manually, this is a nice way for you to do that. There's different ways for you to bridge this, but the expect actuals is as a way for you to define a function and make sure that it's going to show up and all that. And again, this is where we can provide some other wrappers around like our Compose as well. So nothing magical there. When we jump into the game here, I don't want to we don't need to get too deep into the code, but at the end of the day here, we have different composables. It's really hard to navigate around this. We got this big box that we're creating here. This is how the UI is updating, where we can resize our game. So when we look at this game here, that I'm obviously an expert at, we can actually resize it on the fly and make sure that we'll still hit stuff. And so those all change. Go ahead.
Are we supposed to see the game?
Oh, sorry, you're not seeing a game. I'm playing a game, and I was doing really well, believe it or not. So I was doing really, really well in this game. I just share my full desktop. So here's this game that you can now see, and it's just Flappy Bird, but with with some changes here. We can resize and adjust even during gameplay. Which are some really unique challenges that you have to deal with when you're working in, especially on desktop or with the resizable windows. So all of that happens inside of this box, this game main game UI. For this game box, we break this up based on layers that we're going to see. We have the game console. This is like the pause, score, credit things, things that we're going to come up over top of this. But the game box are the layers for the backgrounds, the things that are flying around, and where all that happens. The view model, though, is really what's running all the logic for actually determining the size of things, where we're taking in screen width as it comes in. It's where we're running all the logic for how fast we should be outputting new objects, and where they should be showing up on the screen. But you can imagine that really we're just emitting state objects all the time, and then we're just drawing them on the screen. This is here as I'm actually just showing that there's a JVM run, but this just so because it's quick, but the JVM run is super fast here to work in this space. So Compose Multiplatform, super cool. When you're leaning all the way in, there's a lot of great open source frameworks that you can use that are provided by a lot obviously provided by JetBrains and by Google to help bridge between iOS and Android. But then again, with those expect actuals, you're able to accomplish a lot more if you need to do anything custom. Again, you have the ability to use as much or as little as you desire. So Compose Multiplatform is super cool. Let me jump back in a slideshow here. All right, so there are some nice friction points that we should talk about historically because of the Objective-C headers. Kotlin had to be dumbed down to some of the features that weren't there for Objective-C, but are there in Swift. And so for our folks that are working in Swift, and if we're leveraging KMP, or even if we're leveraging KMP and Compose multi-platform and needing to do something native in Swift, it can be pretty painful, or it was pretty painful. You'd have broken enums because they were converted to Objective-C classes. We would lose generics and they were erased out. Objective-C ignored parameter type for overloads. I actually didn't think that this one was a big deal, and then you realize quickly that it happens more often than what you thought. And so what will end up happening is it creates like these really long names when you're calling the function. So it's really painful. Objective-C doesn't support defaults. And then concurrency is like the big elephant in the room where everything would essentially get handled, passed back to Swift as callbacks, and you're back in callback hell, which I think we all don't want. So Objective-C headers was the way that it worked. And what for many years, I would use, there's a framework called Skia, Ski, whatever you want to call it. I'm sure so folks that created it have a good name for it. But this is how I've worked for years until direct Swift export came along. So in Kotlin 2.3 and above, we can get away from the Objective-C headers entirely. We have direct Swift export, so it solves a lot of problems, but it doesn't solve everything. So we get our enums back, we get our clean overloads, we get a lot of the things where Kotlin and Swift have a lot of similar language features and constructs. So those things come back to us, which is really wonderful. But it doesn't really solve the async. We don't get the default arguments in the same way that we would expect. And so this is where we can leverage the plugin. The Sky plugin is not owned by Google. I think it's Touch Labs that manages that plugin, but it's pretty much industry standard at this point. Again, this is working off the compiler plugin. So when we were talking about before the front end and back end, this is a compiler plugin that is actually just generating the code for us rather than having to work in this the world that we'd have to. So when you combine both of these, we start to be able to use proper async awaits in iOS with cancellation, because that was a big problem. Even when you got async awaits working, then you would have no way to cancel them. So that was fun. Flows are now flows and Kotlin coroutines are async sequences, and then again you get the default records back, which is super great. All right, multi-platform and the age of AI. So, everybody heard about AI? We've heard about the word, right?
No.
Who's tired? I'm tired. I support AI a lot here, and I still get exhausted because it changes all the time. So I certainly don't want to make this talk all about AI, but we should talk about it because that is something that comes up. Is like, do we need to write it once when AI is just going to generate it? Code's cheap now, right? Or at least that's what I'm told. But the difference is that everything around code is still not cheap. Right? We need some level of determinism in the stochastic era that we're in. I wouldn't use an LLM to replace my linter. So why would we expect that to replace everything? So this is a nice unified way to provide some architectural guardrails for the models to work within. And so there's still some great wins there. One of the perks of AI, though, and when we talk about multi-platform, is we can start to maybe remove ourselves from like the language barriers a little bit. I might have been less open to one platform or another because maybe it wasn't my first language, or I don't like working in that language as much. And now maybe if I'm a little bit more open to it, if we're generating more of that code. If I don't have to look at Swift, maybe I'm okay generating it, or vice versa, right? I love them both. I'm just just had to. One of those for us. So hopefully that is something that we're a little bit more open to. That allows us to evaluate multi-platforms differently. We can look at it from what are our actual business cases that we're trying to solve from using it. What are the impacts for our customers in both of those scenarios? And really just making that the right choice for those reasons, rather than what is our favorite language, which is kind of what it comes down to sometimes. And I would still argue that we end up in a unified context state. So we have things like MCP and various tools that are being made available by these companies so that we can operate really well with AI and generate code in this. So I still believe that multi-platform has a space in the world of AI. It doesn't mean that everybody's going to make that choice, but this is how I kind of break that down. And so then we have to make a choice. Do we go Compose multi-platform, Kotlin multi-platform? You may choose none at all. That's okay too. But we kind of have to start to figure out what decision we want to make. And I think ultimately it's going to come down to your application's needs. If I was working in a large app, I don't typically work in a large app at all. But if I was working in a large app, I would probably lean in more on the KMP, leveraging native UI, especially if we're going to be looking at native UI paradigms like Liquid Glass, where some of that is a little bit harder to replicate in the full shared UI space. Compose multi-platform. I have a smaller team. I need to run it in as many places as possible. But I care most about pixel perfect consistency from one platform to the next. Some teams care a lot about that. Some teams don't. So if that's your team, you may care about that. You may want to bring Liquid Glass to Android. Compose multi-platform could work for that as well. There are some frameworks out there that'd be a great fit for you. So if that is your team, or if that's your company's prerogative, that Compose multi-platform is a great approach. But likely, most folks in this room will probably fall into somewhere like the hybrid approach, where they use Compose multi-platform. Back in a previous world, I was doing a lot of retail work. And when I was in that retail work, we leveraged native pretty much everywhere except for on the shopping cart. The shopping cart page is like we always had consistently the most bugs, the most inconsistencies from one platform to the next, where we got in the most legal trouble. And so that is where we focused on our cross-platform capabilities. So you might think of some things like that. So Everybody is going to choose the decision that's right for them, but evaluating it as pretty straightforward as long as you understand the goals of your project. And that is it for me. I'm happy to talk a little bit more about Compose Multiplatform, in the break, talk about the compiler, any other questions, or if somebody wants to play the game for a long time, I'm happy to let you do that as well. But hopefully kind of dispel some myths and set you up to make a right decision. Thank you.
Okay, I think Paul and I said we will give 5 minutes for questions, up to 5 minutes for questions. So does anyone have questions? Yeah, does anyone have questions? I guess Paul, just hand the mic around. Let me know when you're gonna anyone speak. Does anyone in this side have questions to start?
We have one question here.
Okay.
You mentioned specifically liquid glass as kind of a barrier, but how does it handle for like standard problems like collection view reuse or just like other things you leverage from UIKit? Do those things port over also problematically, or are they just rebuilt or?
So they're just So they're not ported over at all, because if you are building with Compose, can you hear me all right?
Yeah.
All right. So if you're building with Compose UI, remember we're just drawing it straight up on pixels. So we are leveraging Skiko for that on iOS, and so we're going to just draw. It's going to use metal instructions, drawing instructions, and it's going to draw those pixels directly on the screen. So there's no UI kit. There's actually no concept of a collection view. So you'd be more likely to see like the concepts of Android, where it's like the recycler view, but they're again being reinvented for on the Skiko drawing instructions. Does that make sense?
Yes.
Okay, good. Question here?
What about accessing hardware like the camera, for instance?
The question here in the room was, what about accessing hardware like the camera? So there's many ways to do that. You don't need to build any of that out. There are packages that you can pull in, but let's assume that those all didn't exist. Those expect actuals that we were talking about earlier, that's what you would do. That's what you would leverage there. But I would imagine like you're talking about also like the viewport for like showing like the preview of the camera as well. Yeah. So again, I haven't actually used that one. This is probably one of those ones where I would build it out natively instead. If I were doing it, because those frameworks are going to run far better.
And expect actuals like I'm going to have a native module essentially.
Yeah. So like if you're depending on like what you're doing, like if you wanted to say like I want to use the camera, I want to launch the camera app, take the picture, and then return the result. The expect actuals are going to be a great use case for that. But if you're actually wanting to create your own camera app, right, and you want the preview, that's probably a use case where I would not leverage either one. I would actually just navigate to something that's pure native Swift code, and you have the flexibility in Compose Multiplatform or in KMP, either one, to do that.
Thanks.
Go ahead.
So how versatile was like KMP during like last summer when we transitioned to liquid glass? Like was it
How versatile was KMP
Yeah.
last summer before we transitioned to
like as we transitioned
or as we transitioned?
was it easy set up?
In what do you mean? In what sense?
Like it integrated natively, like immediately showed up bars at the bottom. Everything just worked out of the box, or were there like
Yeah. I think it just depends on what you're doing. But you have to remember, like it's going to work out of the box. But there's still going to be nuances. Like you aren't going to get the exact Swift UI experiences or native experiences, because we're recreating those in pixels, right? So when you're building it, in this case, Compose Multiplatform, when you're sharing UI, since we're just drawing pixels on the screen, it's going to work really, really well. The biggest areas are like, okay, we're relying on Compose Multiplatform to be there and have all of those capabilities built out. And inherently, we would have something that's available in Android that's using Compose, but it wasn't yet multi-platform supported. And some of those still exist today, like a constraint view in Android is not there. And so you have to build that out in some other way or bypass it altogether, or you can find some other open source framework. So since you're drawing pixels on the screen, like it's pretty well there, but I would say it's last year was a good year for Compose Multiplatform and like becoming really stable.
That's awesome.
Yeah.
Okay, so we have one more question in New York, then Anthony on the Zoom, then that'll be it for questions.
Hey, thanks for your great talk. I was curious about, you said that CMP uses Skia under the hood. Now, I know that Flutter also did for a while, and then they moved
Still does.
away to their
Oh, did they?
own engine called Impeller because of issues they had with shader compilation jank at runtime. And I'm just curious if you guys are aware of that, or if you're looking to do something similar, if that's affected you guys at the CMP side. I'm just curious.
I haven't hit issues with that. It's possible that they've made fixes in SkiaCo because again, it's built off of Skia, but it is a fork of Skia. So for Compose Multiplatform, so I haven't hit any of those issues in what I'm building. But it doesn't mean that it's not out there. So I don't have a good answer for you on that. If I'm being honest with you. So, but it's something that I'll take away and take a look at.
Thanks.
Okay, Anthony.
I was curious if you have something like an API key that normally you'd read in like a build config in your Kotlin code, how would that play with multi-platform? Like, would you be able to read something from the iOS build system separately?
Yeah, you absolutely could. You would leverage the expect actuals in order to achieve that. So you have similar builds that's going to run. It depends on like where you're going to use that key and whether you need to locate it like in which build file. But yes, you could provide it in your Xcode project config, or you could put it even in your build.gradle file, either one. And then I would leverage the expect actuals paradigm as well. Or again, if you are calling a function, you could just supply it as an argument in the function from Compose. There's many different ways that you might provide it.
Great. With that, I think we're going to cut it for questions. So once again, a great round of applause for Clinton.
Thank you.
Yeah, so, thank you very much for having me, New York, and thank you for having me, DC. That last talk was fantastic, and I'm basically just going to say the inverse of everything that Clinton just said. So, no, so this is going to be a talk on Swift on Android, which is a very, very new and very exciting place to be in right now. My name is Mark Prudimo. I am a software engineer. I've been making apps since, forever, since the beginning of app development. I am one of the creators of a tool called Skip, skip.dev. And that is a tool to enable developers to bring their applications from iOS to Android using a single Swift code base. And we've been working on this for the past few years, since 2023. I'm also one of the founding members of the Swift Android workgroup. I'm the release manager for that. So I've been working closely with that side of things as well. And I'll talk a little bit more as time goes on about what the relationship is between the Swift Android SDK and the Android work that's going on as part of the Swift organization, and Skip itself, which are two completely distinct entities. I do not work for Apple. I don't work for Google. I'm completely independent. So the agenda of this talk is my microphone okay? I feel like it's cutting out a little bit. Is everyone okay? Great. So the agenda, quick intro, 3 parts: how the SDK works, what you can kind of do with it right now, and then sort of how you can complete the picture with Skip, and then a quick conclusion. So People probably heard last month, late in March, Swift 6.3 came out, and one of the headline features was Android support. And a lot of people sort of took a double take and said that that wasn't on their bingo card for 2026. I would counter saying that people did not do their bingo due diligence, because Swift on Android has actually been in progress for a very, very long time, over 10 years. Even since before Swift was open sourced, people were tinkering around with getting it to work, just like kind of digging into the low level, LLVM, Clang, interactions, be like, can we get this to output a binary that will kind of work on Android? And it's always been sort of a random, collection of kind of start and stop efforts, a lot of, names, some of which you may have heard, CompNerd and Finnegalfin, and, a wide variety of different people have, spent a lot of time sort of trying to get it working. Some people have stopped work a while ago, but their work sort of was picked up by others and continued on. But it was always sort of in the kind of like out there gonzo, sort of work stuff. No one really considered it to be an especially likely scenario that this was going to be somewhere that that Swift wound up. But then in 2023, 2024, they came out with the cross compilation SDK support. Has anyone here used any of the cross compilation SDK, like cross compiling from macOS to static Linux or to WASM or anything like that? Okay. So I'll talk a little bit about the concept of that, but it's surprisingly similar to what you're doing every day as iOS developers, as I imagine almost all of you are here. Are there any Android developers here? There are 1, 2, okay, 3, 4, and I imagine most of the rest of you are iOS developers. I'll just assume. So that was really the thing that opened the door, the cross compilation SDK, SE0387, to enabling this to become an official part of the Swift language, of the Swift community. And then last February, I got together with Yanis Orlandos, who does a lot of Swift on Server work, and we started the Community Android work group, which was essentially just saying, we're just going to start doing this. And then fairly quickly after that, we got sort of endorsement from the rest of the broader Swift.org community. And we started the official Android work group, and that's was chartered, and it's one of the work groups like Server, C++, all the other work groups that are kind of trying to build out Swift, so that it really expands out from its origins as kind of an Apple parochial set of tools. And then in October, we started publishing the first official nightlies, and then just last month we published the SDK along with Swift 6.3. So that's a very quick tour of sort of like how it's evolved and how it sort of came to be. So the Android work group itself, as I mentioned, is an official Swift.org work group. Has its own web page. Has a charter and everything. Has a a group of members. Is I think 8 of us or 10 of us right now, and we essentially are working to enhance the support, make sure it stays stable, make sure it stays tested as part of the official continuous integration, make sure every release of Swift that comes out also has the Android SDK going along with it. You can read all about it on the Swift.org website. And as I mentioned, Swift 6.3 is the first release that came out with Android support. I'm going to talk a little bit about what actually that means. So part 1, the Swift SDK for Android. So, as iOS developers, you probably know this top row back to forward. You don't really think about that much about it, but say you have, an Xcode project and maybe that embeds a Swift package manager, or maybe it's just an Xcode project, but you hit build and run, and there's really 3 distinct steps of things that happen. The first is a compilation, right? It takes your Swift and it compiles it, to native object files. The next is a packaging. It basically takes all that Swift, takes all the related frameworks, it bundles it all up into an IPA. It takes all the resources, it puts it into this, zip file that holds your application, and then, it assigns it if you're putting it on a device. And then the final step is that it deploys it and activates debugger. So it takes that IPA zip file and it plops it onto your simulator on your device, and it launches it, and then it interacts with it. You can see the console and stuff like that. The Android world is essentially identical when you're developing a standard Android application. Generally speaking, in Android, as we talked about in the last talk, you'll usually develop using Android Studio. And so, you'll hit build and run, and it kind of has those same 3 steps. It takes your code, on Android, as we mentioned, that code is typically Kotlin or Java, but it will compile it to, binary code, and it'll go through a packaging step that'll typically use a tool called Gradle, which is kind of the Android world's equivalent of Swift Package Manager. And that'll do using the Android Gradle plugin, that will do all of the bundling of assets, all of the assembling of dependencies, put it all into a APK file, which is the Android world's equivalent of an IPA. They're both just zip files full of, code and resources. And then it'll assign it if it's putting it on the device. And then again, it connects to your device and launches it. So where does Swift fit into this scenario? So with the cross-compilation SDK, what Swift does is it interacts with the Android SDK component called the NDK. The NDK is the part of the Android build system that handles compiling native code, right? So it's not compiling Java, it's not compiling Kotlin. It's taking your native code and it is compiling and linking it into one of the supported architectures that Android, is currently supporting, and those sort of come and go. So I'll hop to the next slide because that will. This is probably a little more details than we need, so I'm going to skip over it. But this is kind of the overview of the Android SDK. There's kind of 3 different parts. There's the tooling, how you interact with your device, your emulator, the platforms, the APIs, the jars you interact with, and then the NDK itself. And the NDK is the part that the Android SDK hooks into. The cross-compilation SDK takes your Swift and uses LLVM to compile it. And then that communicates with the NDK's own cross-compilers that will basically take your native code and compile it on, say, a Mac or a Linux machine, and build that for the target architecture that you're building for. There's 3 primary ones that we support right now. There's 4 in total. There's AArch64, which is ARM 64-bit, AArch v7, which is ARM 32-bit, which is a lot rarer now, but still does exist, especially in low-end devices, like a point-of-sale terminals and things like that. There's x86-64, which is Intel's 64-bit, which not a lot of handsets have, basically 0, but like a Chromebook does. And also, if you are running your build tools on an Intel machine, on, say, a Linux Intel machine or one of the older Intel Macs, your emulator will be running using that same processor architecture. A little bit like how the iOS simulator back in, the days of, Intel Macs, that would actually be running on the Intel architecture. And then there's 32-bit x86, which we do not support in the SDK because essentially there's no existing devices out there that still support it. So how do you get the Swift SDK, into your system, right? Like, does it come with Xcode? No, it does not. Xcode just comes with, the standard Apple SDKs building for, iOS, iPad, Mac, and things like that. The SDK comes as part of the open source Apple toolchain. Now, no one here raised their hand when I asked if they had used the cross-compilation SDK. So has anyone ever installed? Okay, we got one person. Has anyone ever installed the host toolchain separate from Xcode? Oh, we got a couple. Okay, so as you know, Xcode comes with its own toolchain, but there's also a mechanism for installing a host toolchain that's outside of Xcode. That's actually a completely separate, independent line. Over time, they're going to be merging these, perhaps in the 6.4 later, time frame. But right now, it's sort of 2 separate parallel worlds. So you can actually have 2 separate versions of Swift building on one machine. The cross-compilation SDKs right now only work with this, open source toolchain version of things. So there's a variety of ways of installing and configuring it. You could just install the binary zip yourself, but the standard way is using a tool called Swiftly. So if you're ever to go to landing page of swift.org, and and see the install Swift, this is what I would recommend that you do is install via Swiftly. Same with Linux. So Swiftly is sort of a Swift toolchain manager. And then you can install, the certain version, the most recent version is 6.3.1. That's that top line. And then next, you install the SDK, which is an add-on to your existing Swift installation. And then you can see where they describe how to do that. It's down in the Swift SDK bundles. And I mentioned that Android is the third one that they made available. Previously, they had the Swift static SDK for static Linux, which is super useful because you can compile like a server application on your Mac OS device that will be a statically built Linux executable, and you can just copy that over to your server or your AWS image or whatever cloud provider you have, and it'll just work because it's compiled. So that's an example of how cross compilation is useful. The Swift SDK for Android is the same kind of layout. It's an add-on to the Swift SDK. So you do that, and then once you have it, then you can run like Swift SDK list, and that will list all of your SDKs. It'll list Android. If you have the WASM SDK, it will list that, the WebAssembly. And then you can essentially start compiling using that. So, here's a very simple example of a hello world, source, file. It's just got a main, it just prints out hello world. If you were to, from the command line, just type Swift run hello Android, it would just build that and it would spit out on your Mac, hello Android. If you ran with the Swift SDK argument, then it would find your locally installed SDK that matches that particular target architecture. In this case, we're compiling for ARM, 64-bit ARM, which is what AH64 is. But you could swap that out for x86 64 if you were compiling for an Intel. And then you build that, and then you take that binary that was built, that will go into your .build folder, and you can move it over to your Android device or emulator. ADB, that's one of the tools that comes with the Android SDK. That's the Android device bridge, and that's basically a way you can talk to your Android emulator, run a shell on it, copy devices or copy binaries over and things like that. And then you can just run it, and then it will say, hello from Swift on Android. I could do that, but it would take a few minutes. So I'm going to skip over it, but take it on faith. This is in the getting started guide for the Swift Android SDK, which I actually wrote and maintain. So you can be confident that it actually works. I don't think it's, yeah, here we go. The getting started guide for Swift essentially has all of that. Oops, sorry. Okay, so that's like a little hello world binary. It's kind of neat, but it's just a hello world. Actually, running test cases for your package, that's another thing that you're able to do right now. Like say you have a standalone independent Swift package manager package and you want to run the test cases. It's doable, but in this scenario, I'm actually using skip as a front end for it because there's no convenient out of the box way of doing it. You essentially have to compile stuff manually. You have to copy a bunch of files up to your emulator. You have to execute the test case executable with a lot of weird flags. So in this scenario, this is one of the examples where skip sort of is acting as a front end for it. And skip can just be installed using Homebrew. It's one of the Homebrew core packages. In this example, we run skip Android test, and that kind of does all that for you. It takes your package manager test. It supports both XC test and Swift testing. And then you copy it over to the device and you run your tests, and then you'll get the output. So that's really important. If you ever want to be porting your own packages, make sure they work okay on Android. That's what you'll be doing. And that's what we're doing right now with CI for a lot of the Apple packages, a lot of the Swift Lang packages like Swift Collections, Swift Systems, Swift Argument Parser, things like that. That's the core of the CI that happens on every pull request that takes place to make sure that these things continue working on Android just like they do for Linux, just like they do for Mac OS and all the other platforms that are supported by these packages. So overall, this is really the low-level kind of raw stuff you can do with it. This is kind of what's provided out of the box at this point with Swift 6.3.1. You can build your packages on on Mac and on Linux. And actually also on Windows, it's done a little bit differently because the Windows support predates the Swift cross compilation SDKs. One of the things we're hopefully going to be working on will be kind of converging how all of that works together. And then you can compile for any of these target triples. As I mentioned, the ARM versions and x86. And then it just spits out either an executable or a shared object file. So we'll talk a little bit more about how you then take it to the next level and actually how you build an app with it, how you include it in your application. So, what do you get with the SDK and what don't you get? So the cross-compilation SDK comes with a bunch of modules that you kind of expect to use as someone who's familiar with building applications. Like everyone, I'm sure, is familiar with Foundation. You import Foundation, and you can do all sorts of neat stuff. You can have a JSON parser, you get URL sessions, stuff like that. So here's what comes with the SDK. You've got the Swift standard library. It's kind of obvious. You have all the collections, you have strings and stuff like that. You have Foundation Essentials, Foundation Networking, and Foundation XML. Now, if you are coming at this from iOS, you might say, what are those things? There's just Foundation. And you'd be right. On iOS, those are all one single framework. On non-iOS platforms, including Linux, including all the other platforms that Swift supports, those are broken up into multiple different packages under a single umbrella called Foundation. But you can include subsets of it, and that'll be important for maintaining app size. And I'll get to that in a little bit. As I mentioned, you have Swift testing and you have XC tests, so you can run test cases. You have concurrency and you have dispatch. So you have full support for async await and all the dispatch functions. And you have observation, so you can have observables, both older observable object and also the observable macro to be able to track fine-grained property access and your view models, essentially. And then that bottom line, what don't you get? I mean, the answer there is you don't get anything else. So, you might be like, great, can I, import UI kit? Can I import sprite kit? Can I import, no. Nothing that I haven't listed there, you can't import. So this is not some, magical porting of all of the, wonderful Apple frameworks. Some people say it's like, great, I've got this HealthKit app. I'm going to port it, drop it onto Android, and it's just going to work. It's like, well, you've got a little bit of work ahead of you because you essentially have to port HealthKit yourself. So that's important for sort of level setting, maintaining realistic expectations. What do you get out of the box? You get these important things. Now, I mean, as we know, Foundation does a lot. Like, you can, with Foundation and some support for a UI layer, you can basically build a complete application for, a large swath of applications out there. But for all of these very Apple specific frameworks, you have to know that you're on your own there. You have to figure things out. I mean, you're not on your own. Like, I'm here to help, but you're not getting anything for free from the SDK there. So I talked a little bit about showing a hello world, right? You can build a little command line executable, put it on your device, run it. It's like cool, but like that's not what we want, right? We want to run an Android app. Like we want a thing that comes up on the screen and has buttons and sliders and navigation and lists and things like that. So just being able to put a hello world on the device is not really what we want to see. What we want to do is we want to build real applications, and as I mentioned before, those are APKs. The equivalent of an IPA, a zip file of code and resources. And the mechanism by which that's done is, Swift compiles to native code, and those are referred to as JNI in the Android world, Java Native Interface. And it's, very well supported. It's completely standard going back to the origins of Android. Most games, high performance intensive games will be using JNI just for performance, to be able to, not have to use garbage collection and suffer some of the performance and memory consequences of that. So as far as Android's concerned, these shared object files, they are just standard JNI, libraries. There's nothing really special for in terms of how Android views it, as if you had compiled C code or C++ code or anything else, Rust or something. And so these get dropped into a folder called JNI libs, and there's one subfolder for every architecture that you're building for, and then that all gets bundled up into an APK. Here's kind of the structure of how an Android application looks. You've always got this top level Android manifest XML. That's all the sort of the info plist in the Android world. It's got like your application name and the current version, stuff like that. It's got your bundle of classes. They call it classes.dex. That's all the Java and Kotlin that you may have included in your application. That's sort of the standard place to put it. And then you've got resources and assets. And then you've got these JNI library folders. You've got one per architecture. And as you see, I only have a subset of things here, but like say you had my app and you use the cross compilation SDK to build that library, it would spit out libmyapp, .so. You would be putting that in your APK, and you'd also be including every one of the dependencies that comes with it, right? Because unlike iOS, unlike all Apple platforms, they don't come with Foundation pre-installed, and there's no standard place where it is shared on the device. So every app needs to bundle it, itself. And that's one of the reasons why subdividing up Foundation can be a significant space savings in terms of the size of your app, because you can just use the parts that you actually need. So that's sort of how it's laid out there. And so you've got your zip file, it's got your code and resources, and it's all in one place. Then what happens? So that's when you get into something called JNI. As I've alluded to, and as you probably know, Android is a very Java-centric platform, right? Everything, all 95% of the SDK is Java only. So to do anything to talk to, so the NDK, the lower level stuff, does have some support for talking to reading assets and things like that, but there's it's very, very limited in terms of the broader things you want to do, any interaction with the metadata for the system, most drawing and things like that. That's all going to be going through Java. So we're talking about talking between Java and your native Swift code in order to make a realistic Android application. You could do sort of like a toy, draw hello on the screen, maybe using pure Swift, not a line of Java. But beyond that, any realistic Android application is going to be using a fair amount of Java. So there's a few different ways of going about this. You could just write the JNI by hand. Has anyone here ever worked with JNI? Okay, yeah, we got a few. So it's not fun. It's a venerable, it goes way back to the late 90s. It's here to stay. It's just the way that Java talks to, the native world. And it's, it has stood the test of time. It's super robust, but it's real persnickety. It's very much a C-oriented. There is a sort of a C++ view into it, but it's a very C-oriented thing. And it's very, anyone working with it for any serious amount of time needs to have something that handles these bindings for you and bridges it, because no one wants to write it themselves. So there is a project ongoing right now. It's the top level Swift Lang project called Swift Java. And that is the project that allows you to automatically generate bindings that talk to and from between the Swift and the Java. So that's sort of ongoing, and that's a way where you can get kind of low-level integration with some of the Java stuff. And I'll move on to talking about sort of the view that Skip takes of all of that. How am I on time? I have a few more minutes. Okay. All right. I'll breeze through. That's fine. Okay. Yeah, I'll breeze through. I'll skip over a couple of slides. Okay, so that kind of gives you a sense of where we're at today and where sort of the standard support for doing things are, and what you get out of the box. Building on top of that is open source technology that I work on called Skip, and that's a mechanism for taking your Swift UI code, just a single code base, sort of completing the stack and being able to compile that onto Android. And run a full application. So essentially, you take You install skip, I showed you how to install the low-level layer. You add it as a package Swift package manager dependency to your package, and you run the app. It uses the build plugin system that was added to Swift package manager a couple of years ago, and it takes your code and it automatically generates any bridgings that it needs. And it also provides its own libraries that bridge Swift UI down to Jetpack Compose. So it is able to. I can show you sort of how a package looks when you're using skip. And so you have the skip plugin, which is called Skipstone down here. And then in this particular example, the showcase example, I've got a bunch of other libraries that support various things like the AV system, embedded web browser, keychain, and things like that. And then the way that it looks, you've got your iOS simulator right here. And then the Android emulator that I alluded to earlier is basically the same thing. Okay, cool, it already launched. Is the Android equivalent of the simulator. And so here there we go. So we've got the iOS version. So you can see on iOS, it's just Swift UI. It's just like Skip is not doing anything at all. It's just vanilla, Swift UI. On Android, it takes your Swift UI and it converts it through to Jetpack Compose, which is essentially Android's equivalent of Swift UI. So you have a lot of automatic, support for all of the system things. You've got, as you can see, you've got Liquid Glass right here. You get Liquid Glass menus and stuff like that. And you've got, navigation, you've got searching. I mean, there's a million things here that you can play around with. And this is actually available on the, let me get back to desktop 5. This is actually available on the App Store, both the Google Play Store and on the Apple Apple App Store. So it's really nice if you ever wanted to be evaluating this sort of technology to show people, okay, this is how a button looks here and a button looks here, this is how this behaves, this is how navigation works. It's nice to have these two side by side so you can bring them up. And this is built fully as of the release of the Swift 6.3 SDK. This is fully built on the actual released SDK. Earlier versions were out there with preview builds that we had managed ourselves, but right now this is actually using the canonical build. So it's a great way to basically show, like, look, you can really build a real application with this. You can, actually get something up and running. So yeah, so I definitely, and at the end, I'll provide another link too that you can go to be able to look more closely at all this stuff. So, I want to sort of wrap up by talking about the broad overview of this, space of cross-platform, the cross-platform landscape. I'll actually jump to this one. So, I would say right now we really have 4 kind of major players. I mean, there's a bunch more, right? There's older ones like Ionic. Xamarin has been kind of deprecated, and Maui does not seem to have quite caught fire yet. So you're really left with the choice between like React Native, Flutter. On the Kotlin side, you got KMP and CMP, which we now know all about from the last talk. And now we have the Swift, possibility for cross-platform development. I think a lot of people know, React Native and Dart. Those are all uniform colors because those are all just sort of like one whole big thing, right? Like React Native, you don't generally write business logic layers and a separate layer on top of it. You kind of take the whole enchilada. Kotlin, as we learned last time, you do have 2 different options. You've got the business layer option, for Kotlin multi-platform. And then on the Android side, it's just Kotlin, Jetpack Compose, like Kotlin multi-platform is not really doing anything. And then on the iOS side, we heard all about how it uses, Skia and rendering to the canvas and sort of the benefits and disadvantages of that. And then on the Skip side, essentially, as I was saying, it's essentially the inverse. On the iOS side, it's just Swift. There's nothing, doesn't even know about Android. Like if you have any Android guards, they'll be within like if platform, OS, Android, and Swift just won't even see it. It'll get compiled away. So then the big question is like, what do you do on the Android side? And sort of the goal of Skip is that we complete that picture. We provide the Android native, layer on top of it for the user interface. And one of the advantages I will say is that on both platforms you have the recommended user interface. The sort of the weakness of Compose Multiplatform, as we heard, was on the iOS side. It's not really like an iOS app. It's really like a material design Android app drawing pixels on the iOS screen, which for some apps I'm sure is fine. For other apps, it's not going to feel quite right, and it might have some performance issues. I do want to make sure I'm realistic and not oversell it, right? I'm a big booster of this technology, as I'm sure you are all aware. And it does have a lot of, big advantages, on the iOS side, primarily, like, it doesn't really do anything. So you're just kind of like, as if it was regular iOS. On the Android side, some of the disadvantages are you are, building and bundling these as native libraries. It is a non-trivial increase in the size of your application. There's a lot of sort of questions around like, what do you mean? Like, well, you compile for 3 architectures, it includes in the APK, but then when you put it up in the store, before it transmits it to the end user's device, it'll compress that stuff and thin it down. So getting an actual like what is the size impact can be a little more challenging than it first appears, but ballpark, you're looking at around a 50 megabyte extra size, which, for some apps maybe is not a big deal. For other apps, little apps, you're like, my app is only like 2 megabytes. Why do I have 50 more megabytes? So that's definitely a focus of what we're working on in the Android work group. How can we get that size down? There's a lot of questions around like internationalization and things like that. Definitely something we're working on. Debugging is the other real Achilles heel. The debugging story is just not very good right now. If you get a crash or something like that, you're kind of in the world of like println debugging, digging through stack traces in the log files. So that's definitely an area where you've got there's some work left to be done. But overall, I think it's fantastic. Here's a list of resources. I'll try to get this slide to the organizers so we can get that up there and shared. But I did want to do just one final thing, which is a little Easter egg that we added to Skip Showcase for Easter, just to see, you can do all sorts of just regular Swift UI, stuff in this application. But you also have a little, and this is actually pure Swift UI, believe it or not. It's just like doing drawing and things like that. And then on the Android side, you have exactly the same completely maddening game. So this application is totally open source. You're welcome to take a look at the implementation of it. It's called like Game Playground. It's like a little less than 1,000 lines of raw Swift UI code, but it's sort of delightfully perverse. And yeah, you can download this on both iOS and Android for your device. And I don't know what happened there. For iOS and Android, and you can play it for yourself. All right, so hopefully it's a quick whirlwind wrap up. But yeah, thank you all very much. I suspect I might not have time for questions, but I will be around afterwards to talk to people. So.